So I want to talk about this theorem that if you have a linear map T from V to W and V is finite dimensional, then the dimension of the kernel plus the dimension of the image is the dimension of the domain vector space. Kernel is defined the same way as for abelian groups, so it's all the vectors that go to 0. If T is given by a matrix, then the kernel is called the null space. And the dimension of the image of a linear transformation given by matrix multiplication is called the rank of the matrix. So this is also called the rank-nullity theorem sometimes. That the dimension of the rank of a matrix plus the null dimension of the null space is equal to the dimension of the domain vector space. So the number of columns of the matrix. Okay. But maybe we should talk a little bit about making new vector spaces from old ones. So I have 3 operations here. One is if you have a vector space over F, you can take a subspace. You can take direct sums like you do for abelian groups. So you just remember that vector spaces are after all abelian groups. So I can just take the direct product of the Cartesian product of the two sets. So ordered pairs V comma W, where V comes from V and W comes from W. And I can define addition component-wise and scalar multiplication component-wise in the most obvious way. And this makes V plus W into a vector space called the direct sum. And you can identify V inside V plus W using V goes to V comma 0. So it's like saying that if you R plus R2 is isomorphic to R3, you know. So like here is R2 and here is R, which is completely disjoint from it except at the 0 vector, and then together they make an R3. And you can identify an R inside there using taking the X to X comma 0 0, and this X comma 0s, and this identification is X comma YZ you think of as XYZ. That's the identification of R plus R2 with R3. Yep. This is all usual stuff. And the quotient construction also goes through like in abelian groups. Again, a vector space is after all an abelian group. So V is a vector space, U is a subspace. Then you can make V mod U, a quotient vector space. The elements are exactly the cosets. You just have to show that there is a scalar multiplication defined such that alpha of a V plus alpha of the coset of V is same as the coset of alpha V for all V in V and all alpha in F. And then you have this quotient map taking an element to its coset, and this is a surjective linear map, and its kernel is exactly U. So all this goes through in the usual manner. Rather than prove this theorem directly, I want to sort of introduce a little language which gives a lot of mileage in more general context. It's called a short exact sequence. So I want to introduce this notion of short exact sequences. A short exact sequence of vector spaces is a sequence, is 3 vector spaces, UVW and 2 linear maps. An F from U to V and a G from V to W, such that F is injective, G is surjective. So F is 1 to 1, G is on to, and the kernel of G is the image of F. It's a mouthful. Let me break it down. So the picture is you have 3 vector spaces and 2 linear maps like this. This one is injective, which is denoted like so, and G is surjective, which is denoted like so. And you know that kernel of G is image of F. So the cartoon that I want you to have in mind is here is V maps onto W. It has a 0. So the things that go to 0 under this map is the kernel of G. That's exactly the image of F. And F is injective, so U is actually isomorphic to this kernel. Here is F, here is G. And this sort of short exact sequence come up. I'll give you 3 examples. The first one from direct sum. So you make a direct sum of VW, 2 vector spaces, and then you can identify V in there, like I said. On the other hand, you can project this to W, projection onto W, taking VW to W. That's an onto map. And what is the kernel of this map? This is exactly the things that, what are the things that go to 0? It's exactly the things that have the form V comma 0, which is the image of the first map. Another example, when you have this quotient construction, you have V and a subspace. So this is just the inclusion now. And then you make the quotient. Oops, V mod U. This is the quotient map. The quotient map is an onto linear map. The kernel is exactly this guy. So this is again a short exact sequence. Third example up here, when you have a linear map, any linear map, you take V, T may not be onto, but if I restrict it to the image, then by definition it's onto. And what is the kernel? It's the kernel of T. The kernel is a subspace, so I can again take the inclusion, and the kernel of this map is exactly the image of this inclusion map. Yeah. So this sort of short exact sequence does show up. The theorem that I want to prove is let be a short exact sequence of finite dimensional vector spaces, then the dimension of the middle vector space is equal to the dimension of the 2 end vector spaces. In fact, more is true. In fact, V is isomorphic to, you can try to prove this, V is isomorphic to U plus W. But we won't, if you can prove that, then the first thing follows, of course. But we'll just indicate how to make a basis. So I want to show, and this is rather interesting argument, so let's sketch the argument here a little bit. By the way, if you can prove this, then then you apply it to that short exact sequence, then you immediately get your Rank-Nullity theorem. The dimension of the kernel plus the dimension of the image is the dimension of V. You also get things like dimension of a quotient vector space is equal to dimension of V minus dimension of U, applying it to this short exact sequence. The dimension of V is dimension of this plus dimension of that. So here's the sketch of the argument. At least a little bit of it. You have F, then you have G. Let's say I give you a basis here, and I give you a basis here, U1, U2, Um. Out of that I'm going to make, out of this data, I'm going to make a basis of V. What I do is I just take pre-image. So given. So let's write something here. Choose little vi in V such that G of Vi equal to Wi for I equal to 1 to n. So I choose V1, V2, Vn that go to the W's when you apply G, and I can do that because G is onto. On the other hand, I have these U's in U, I apply their F, so I get a bunch of things here. The claim is that these guys together that you see here form a basis. V1, V2, Vn, F U1, FUM is a basis of V. So the dimension of V is going to be n plus m, where the dimension of this is n and the dimension of this is m. That's why the dimension adds up. Okay. Now let's just see quickly why they span, at least how to see. So you give me a V in V, and I need to write it in terms of these guys. Right? You look at GV, apply G. That's the element of W, so you can write it in terms of the W1, W2, Wn. What that tells you is that if I take V and subtract out the corresponding combination of the V's, then G of that is G of V minus alpha 1 W1 minus alpha n Wn, which is 0. So this thing is in the kernel of G. So this thing is in the image of F. That's the main condition, right? The kernel of G is in the image of F. So this thing is F of some vector in U, some U in U. So you can write this as F of some the U can be written in terms of U1 to UM, so you can write that in terms of some beta 1 U1 plus beta M UM. But now you have written V as alpha 1 V1 plus alpha n Vn plus beta 1 times F U1 plus beta M times F UM. See, you have written V in terms of the VI's and the FUI's. Exactly in terms of these. So these guys span. And a similar argument going back and forth show that they are also linearly independent.